Okay, today we're gonna continue with graphs. And we're gonna go over a minimum spanning tree, shortest paths for weighted graphs, some known graph problems, which is good to have in your mind. And then we're gonna cover a bit some special graphs, like trees, directed acyclic graphs, and bipartite graphs. Now, moving away from unweighted graphs, we can now have edges which have weights, and this could represent the distance of a road, the cost in money, perhaps, of going over the edge, like crossing a bridge, or it could just be some capacity of the edge, like how much water can flow through a pipe. And we can modify our adjacency list to represent these weighted graphs. We can define an edge going from u to v with a weight variable. So again, you can have positive edges, edge weights. The weights can be 0, they can be negative, they can be decimal numbers, they don't have to be integers. So then here we just push back a couple of these edges, representing all the edges in our graph, using our class which we defined. Okay, let's move on to the first problem. So, a minimum spanning tree. If we have an undirected weighted graph, then the vertices, along with a subset of the edges, is called a spanning tree if it, first of all, forms a tree, so there's no cycle, and secondly, the tree spans all the vertices, so it's a single connected component. Now, the weight of this spanning tree is just the sum of the weights of the edges which we selected, and we want to find the minimum spanning tree. And here a couple of greedy algorithms work. One in particular is Kruskal's algorithm. There we sort the edges by weight, and then we iterate through them in increasing order. We then just greedily pick the smallest edge if it is not already, if the two vertices are not already in the same group, to check if there's a cycle. So we use union find for that, to do that quickly. And when we've gone through all the edges, we have a minimum spanning tree. We're gonna make n-1 union operations in total, which is corresponding with us having a tree. There are only n-1 edges.
So is the idea with the union find is that before you add an edge, you see whether or not the vertices you would connect are part of the same subset that you're already keeping track of?
Yes, and if they are, then adding the edge would create a cycle. because if you are connecting A and B, and A is already reachable from B, then adding an edge between them will give you two paths to B, therefore forming a cycle. Now, the time complexity of this is just bounded by the sort operation, which is n log n, and since we're applying that on the set of edges, the time complexity is number of edges log number of edges. So here I have defined a comparator for the edge class which we made, and it simply compares the values of the weight variables. So you get in two values here, a and b. If a is less than b, this function should return true. Then in our MST function, we have n as a parameter, just the number of nodes or vertices, and then the list of edges. So we define our union find, we sort the edges, and then we create a list which will contain our answer, so what edges we selected. Then we iterate through the edges, we get u and v, and we check, are these already in the same component? If they are not in the same component, then we add the edge and then push it back to our result vector. So here we are always greedily taking the least value, and this has been proven to be an optimal answer. Then we have shortest paths. So we have a weighted graph. It can be undirected or directed. And we want to know what's the shortest path from the vertex u to the vertex v. And of course, if all the weights are equal, then you can solve this with breadth first search. But that's of course a very specific case. And there are many known algorithms to do this for different cases. And usually these algorithms have a starting point and then they find the answer for all destinations. So you find the shortest path from a start vertex to all the other vertices. Now we're going to look at Dijkstra's algorithm, Bellman Ford, and Floyd-Warshall. So here we have code for Dijkstra's algorithm. We have a priority queue to maintain what is the least distance to a node that we have seen. So which node which we have seen has the least distance value associated with it so far. And to begin with, we have the node start. So that's just the node which we have selected to start at. Then this is very similar to breadth first search, except we're using a priority queue. So we pop the front of the queue, so the value with the least distance, or the node with the least distance, And then from there we expand to other vertices. We check all the neighbors, and if we find a better distance value for a neighbor, then we update it, and of course add it to the priority queue. So the time complexity here is O of V log E, and this only works for non-negative weights, because if you have a negative weight, then suddenly you can go from a higher value to a lower value, and then our priority queue ordering isn't guaranteed to work properly. The key idea here is that you can go through the distances in increasing order because everything is positive, or not everything is non-negative. If you have 0, it's still fine. We have the Bellman Ford algorithm. So here we do n-1 iterations, and in each iteration we update the distance to each node. So we start with having just our starting node, and then in the first iteration we will go through all the vertices, go through all of its neighbors, and then update, okay, what is the minimum distance to node V from the start if we take at most I steps. So here the minimum distance is gonna be, well, either it's the value that was there before, or we can go from U plus the weight of the edge, and that'll be a better answer now. So this works for negative weights as well. However, it is slower. So the time complexity here is O of V times E. And this can be used to detect negative weight cycles. Because if you do another iteration here and something changes in value, something gets lower, then that means that there's a negative edge weight cycle. Since from every node, you can get from every node to every other node in n-1 steps. So you only need n-1 steps to calculate the correct value. And then if you add another step, the only way that would decrease the value of a node is if there's a cycle which you can take which reduces the distance. Finally, we have the Floyd-Warshall algorithm. And this is a dynamic programming algorithm. So we let SP, that's for shortest path, of k, I, and j be the shortest path from I to j if we're only allowed to travel through the vertices 0 up to k. So our base case is 0 if the vertex I and j are equal. We also have the weight of the edge from I to j if we're not allowed to use any vertices here. And then if there isn't an edge between them, then that will be infinity. Then at each step, we have two options, really. So either the previous answer is better, and we don't use vertex k, or we use vertex k, and so we say we're only allowed to use vertices k minus 1 for extra travel. We find the distance from I to k, and then we add, if we're only allowed to travel up to k minus 1, we add the distance between k and j. So here we're including vertex k, and here we're excluding it. And either of these is going to be optimal. So this is just going to be 2 nested for loops for initialization, and then 3 nested for loops for the calculation itself. And this will give you, so the advantage of this is that it gives you all pairs shortest paths. So you get the shortest path from A to B for every single A and B. You're not defining any starting vertex. Time complexity is clearly cubic. We have these 3 loops, each of them go up to n. So this is going to be cubic. And another advantage of this is it's really simple to code. So let's shorten it using our macros. So it just ends up being this, just 4 lines of code essentially. Now, let's cover the known graph problems. So these can be hidden in problems as just a tiny subproblem, something you have to solve after getting some info from the initial input. And it's good to have an idea how to solve these. So let's look at a few examples. So we have the minimum vertex cover problem. So if you have an unweighted, undirected graph, then what we want to find is a subset of the vertices S such that each edge, well, for each edge that we have, so UV, either U or V are in this set. And I think a picture makes this a lot clearer. So this vertex here, by selecting it, we are covering it and all of its neighbors. So we covered these 3 already. By selecting this one, we cover this one, this one, this one, this one, and this one. So we cover all of these. And by selecting this one, we cover this one here, these these two. So that's why it's called the vertex cover. If you select the vertex, you are essentially including it and everything that's connected directly to it in the set. And usually what we want is the vertex cover, or a vertex cover of minimum size. There can be many. So for example, if we select these two nodes instead, then this one covers these and this. And this one covers this one. So this is an NP-hard problem in general graphs. And then we have the maximum independent set. So again, we have an unweighted, undirected graph. And an independent set is just a subset of the vertices where no vertex has where no two vertices have an edge between them. So none of them are adjacent. So for example, 2, 3, and 5, there's no edge between these. So this is an independent set. And we want to find an independent set of maximum size. So like so. And this as well is an NP-hard problem in general graphs. So these two problems are very related. A subset of vertices is a vertex cover if and only if the complement of the set is an independent set. So here we have the independent set 2, 3, and 5. And then 0, 1, 4 is the vertex cover. Here we have the independent set 0, 3, 4, 5. And 1, 2 is the vertex cover.
But not necessarily a minimum vertex cover.
A maximum independent set corresponds to the minimum vertex cover.
Isn't the minimum vertex cover in this graph 0 and 1?
Zero and 1?
Yes.
These are not weights. It's just the size of the set which matters.
Oh, yeah, sure. So
the size of the minimum vertex cover plus the size of a maximum independent set are going to be equal to the number of vertices. And this is due to the statement about the complement. So everything that was not in the maximum independent set is going to be the vertex cover. And then you have all the nodes. Another problem is maximum matching. So we have an unweighted, undirected graph, and a matching is a subset of the edges such that each vertex is adjacent to at most one edge in the subset. So if we look at this, we can select this edge here and this edge here. And if we have these two edges, then we can't have this one because it has a common endpoint with something that's already in our matching. So we can't add any more edges to this matching, which means it is maximal, not maximum, maximal. But we want to find a matching which is of maximum size. So if we do it like this instead, then we have 3 edges, and this is the maximum matching for this graph. So in Icelandic, this is called spyrðing, because people used to tie fishes together at the end. So sporður, they took it just 2 sporða, bundu það saman. Það var spyrðing. It's a very strange translation. Now, this is actually not an NP-hard problem. So there exists an O of v to the power of 4 algorithm for general graphs. It is pretty complex. It's known as the Blossom algorithm. And I have implemented it with Bjarke, who taught this course before, and it seems to run pretty fast in general, faster than you'd expect from the time complexity. So this is simply a worst case for some degenerate case, which I actually don't know what it looks like. But the basic idea of the algorithm is that what can cause problems with the standard algorithm, the simple one, which is known as alternating paths, is if you have odd cycles. And then if you have a short path in a graph, and then you reach an odd cycle, it kind of looks like a flower. So it's like the blossom of a flower. And therefore it's called the Blossom algorithm, because what it does is it takes the odd cycles and it compresses them into one node. And thus it simplifies the graph without ruining the answer. And it just maintains an extra count of what matchings are in the cycle itself. Like I said, it's pretty complex. Luckily for you, you don't have to learn it and, write it on the final exam. Another problem is graph coloring. So again, we have an unweighted, undirected graph, and a coloring is just an assignment of colors or groups to the vertices, such that adjacent vertices have different colors. So we could, for example, do it like this. Everything has a different color. But we want to find a coloring which uses the minimum number of distinct colors. So note that 3, 4, and 5 can have the same color, like so. And this as well is NP-hard in general graphs. Okay, so all of these problems are hard in general graphs. Even the matching one, although it's not NP-hard. But if we have some special kind of graph, if we know some property of our graph, then maybe it can become easier. So let's look at a few examples. So bipartite graphs. A graph is bipartite if the vertices can be partitioned into two sets, and there is no edge going from set 1 to set 1. They always cross between the sets. Okay, so how do we check if a graph is bipartite? Let's move the vertices here. So now this is usually how we draw bipartite graphs. One set on one end and one on the other. So now you can see here, this is a bipartite graph. So we want to check if we can split these into two groups. So we just take any vertex as a starting point, and we assume that it's in our first group. And then all of his neighbors must be in the second group. And then all of the neighbors' neighbors must be in the first group. And so on. And you can do this with depth first search. And simply what you do is if you ever find a contradiction. So if you ever end up in a situation where you have to say, this neighbor should be in group 2, but it already has group 1 assigned to it, then you know the graph is not bipartite. Okay, so here we have the DFS, and we assign, so here 1 minus side of u. If side of u is 1, this becomes 0. If it is 0, then this becomes 1. And here, if side of u is equal to side of v, so if we're trying to, if our node u is in a group and we've already assigned the same group to its neighbor, then we know it's not bipartite. Okay, and so let's look at coloring bipartite graphs. What if we want to find the minimum graph coloring of a bipartite graph? Well, one side can be colored with one color, and the other side can be colored with another color. So we just need two colors. A common problem is finding maximum matching in bipartite graphs. So tomorrow we'll look at an efficient algorithm for solving this problem. Should do an example of this. So So we can have some edges between here. So a maximum matching here could be, for example, this, this, and this. Or we could have taken this one and this one. So we'll be covering that tomorrow, how to do that. So Kynning's theorem is a theorem that states that the size of a minimum vertex cover in a bipartite graph is equal to the size of the maximum matching in that graph. So to find the minimum vertex cover in a bipartite graph, we just find the maximum matching with this efficient algorithm, which we will learn later, and we have our answer. And since the size of the maximum independent set is just the number of vertices minus the size of the minimum vertex cover, we can also compute the maximum independent set for a bipartite graph efficiently.
So is a matching then the count of the vertices or the count of the edges?
The matching is on edges.
Right. So, but if you have 3 edges, there's a vertex on each side of it. So is it that
Yeah.
the minimum vertex cover is 2 times the maximum matching?
No, it's number of edges. So if you have this vertex in your vertex cover on one side of the bipartite graph, then all of its
Oh,
neighbors on the other side are gonna be, included by having
sure.
this vertex. So yeah, the size of the minimum vertex cover is gonna be equal to the size of the maximum matching, and this is number of edges and here number of vertices. So let me just double check this for you. Yeah, number of edges in a maximum matching is equal to the number of vertices in the minimum vertex cover. Because usually when you talk about the size of a maximum matching, it is a number of edges. Okay. Another type of special graphs are trees. So an undirected graph is a tree if it has no cycles. And we already went over how to check if there's a cycle in a graph. So we can see if it's a tree, if there is no backward edge in the depth first search tree. So in a tree we have n vertices and there are n minus 1 edges. And between each pair, u and v, in the tree, there will be exactly one simple path from u to v. And you can find that with depth first search or breadth first search. So what if we look at these problems for trees? Like how do we find the minimum number of colors needed to color a tree? And turns out trees are actually bipartite graphs because you can pick some vertex and make it the root of the tree. And then vertices which are at even heights can be put on one side, and then vertices at odd heights can be put on the other. So all these algorithms that work for bipartite graphs will also work for trees. Trees are also good for dynamic programming, and there are a lot of problems which become simpler because you can do dynamic programming over the tree. Yeah, directed acyclic graphs. So now we have a directed graph, and we call it a directed acyclic graph if it doesn't contain any cycles. And again, you can check if something is a directed acyclic graph by checking if there are any backward stretches. And again here, many problems are simple on these graphs because it's easy to do dynamic programming on them. So the idea here is if you start at the root, then you're only moving down through the tree. You never go back to a state which you visited before. So you can do dynamic programming, saving the answer of at each node. And even though there are multiple ways of reaching there, you only calculate the value once. So examples of these problems is counting the number of simple paths from U to V, and also finding the longest path. Yeah, maybe another thing to mention is sometimes you can have a graph, just a general graph, which is directed. And a thing to note is you can collect the strongly connected components of this graph. And then suppose you take all these strongly connected components and you compress them into single nodes, just like super nodes, which represent the entire component. Then the resulting graph after this compression is gonna be a directed acyclic graph. Because if there were a cycle in it, then some components would have joined together. And this can allow you to sometimes do dynamic programming on general graphs. It's not always the case, but you can do it sometimes. Okay, so that's all of the lecture today.
For the DAG, I mean, if you want to check, can't you doesn't just a regular DFS suffice?
To check if it's a DAG?
Yeah.
Yeah, it's just check if there's a cycle, essentially.
I mean, if you're going through it and you've seen something you've seen before.
Yeah, that's when you're building the DFS tree, you don't necessarily explicitly build it. But yeah, it's enough to check, okay, have I reached something that I've seen before?
Yeah, I mean, like if you just have an array, right, of have I seen this? I mean, if you go through it, if you find such an instance, well, there must be a cycle.
So it's like I explained yesterday. It's important that you that you store what basically the path you have seen so far. So when you go when you're unwinding the recursion, you have to remove these nodes from the stuff you've seen. Um, Okay, so
it was the example with the numbering of the nodes when you were doing the depth first. When you detect the cycle that you registered the lowest count or lowest number in the path.
You did that at every step.
Yes.
It was not just for the back edges.
Yes, and that would detect a tag, yeah?
Yeah, if there's a back edge. So if you have something that has a higher order and it's going to a lower order, then that's gonna be a cycle.
I mean, I guess what I mean is like it's you maintain just a list of things that you've seen, right? Just like an array of Boolean values. I mean, as you recurse each time, does it not just suffice to say like, ah, have I seen this before? Because if you come across something that's been marked as seen, like it must be it must be a cycle somewhere.
Yeah, but so I'll just show you. So here's the DFS function which does this. Just detects cycle. So
Great. Yeah, I mean, this seems like the basic idea, but as to like why you mark it as false on the way up, that's not clear to me.
So if you're just using the visited, like this array here, which just says I've seen it at some point, then you can take a path to some node. Now note this is in a directed graph. So you can take a path to a node, and then maybe there's another path to the same node, and then you would say that's a cycle. But yeah, I'll just draw a graph for you.
Yeah, I mean, sure, okay, I see what you mean.
So even a simple graph, no, sorry, that's a bad choice of words. So even a graph like this, so you have something like this. So you see, if you start here, you go down here, and you mark this is visited. Then you go up in the recursion, and again, and then here you've already visited this, so you would say this is a cycle, but it is not. So this is why you need to unset in the other array. Set it to false again.
I see. So you're saying if I haven't visited it and there isn't a cycle.
Yeah, so this is just to make sure we don't visit the same state again. If this returns true, so it is not visited, then I check, okay, does the remainder give me a cycle? So calling the function again, and then I return true if that happens. Otherwise, if I am discovering a cycle here, so I have already visited the value. If this rec array at the next neighbor has a true value, so for example, if we flip the edges here, Then going down here, both visited and rec would be true for all these values. And then when we see this edge, we would see, okay, rec of this node is true. So our current stack, or our current path, includes this node.
Mm-hmm.
And we can reach it from our current node. So this means we have a cycle.
I see. Yeah, that makes sense.
Okay, yeah, problem set. So, highest tower and sensor network are the bonus problems. And again, each of the other problems, Breaking Bad, Fire Station, Freckles, Get Shorty, and Vivo Park. These are all valued 1 point, and you need 3 points for full score. So, any questions at the end? Oh, alright, then I'm gonna end the stream.